So we're trying to find 10 different tests for convergence and divergence of infinite series. And telescoping series is one of the tests. Geometric series will be the next of the tests. And this one is huge, guys. This one perhaps is the most important one. It's definitely my favorite. The geometric series are really easy to work with, and they're very nice. And we're looking at kind of the punchline right here. Basically, if you have a geometric series in that we've got to find the next term, we have to multiply the previous term by a common ratio. So we start with some first term a, we multiply by r, we get a times r, we multiply that times r, we get ar squared, and we multiply that times r, we get ar cubed. This is a geometric sequence of values that when we add up turns into a geometric series. And it tells you exactly how to deal with these. If the absolute value of r is greater than or equal to 1, then the geometric series diverges. If the absolute value of r is between 0 and 1, then we can say that the series converges. Not only can we say it converges, we can say it converges to this magic fraction right here. I cannot overstress the importance of this equation right here. In fact, I'll go ahead and include this requirement as well. It's only true if the absolute value of r is between 0 and 1. Now, personally, I would probably include 0 in this. If r equals 0, it's still going to work. It's just not very interesting an example. I can't call myself a teacher, however, and just leave it at that and say, here's the formula, memorize it. I am compelled to show you where this formula comes from because it's such a beautiful proof. So let's go off to the margin and we're going to try to prove this. If we have a converging geometric series, then it converges to a over 1 minus r. Fantastic proof. Let's see if we can prove it. So we're going to start with some, we'll call it S, and it's going to be a geometric series. The first term is going to be some value a. We're going to add to it the next term, which is going to be that value a times some new value r, and then we're just going to keep on multiplying by r over and over again. This is the definition of a geometric series. There's nothing fancy about this. All right, and we have that nth term, but we're going to keep on going forever and ever and ever. Now we're going to assume that this value s exists, and we're going to try to come up with a closed form for this expression. Okay, so here's where the magic happens. Some genius out there somewhere decided, well, I mean, if we're multiplying by r so many times, what's one more r? Let's take this equation and multiply the left side by r, which we're allowed to do, after all, as long as we multiply the right side by r. Now, the only problem with that, it's not really a problem, the only thing we have to remember is that if we're going to multiply a sum by a number, we have to multiply each of those terms, right? So the a gets multiplied by r, and we get ar. I could write the ar here, but it makes more sense to write that here because it lines up with this. And then I multiplied a times r, I got ar. I'm going to multiply ar times r, I'm going to get ar squared. I'm going to multiply ar squared times r, I'm going to get ar cubed. And oh my goodness, this is just going to keep on going and going. We're going to have ar to the n minus 1 somewhere, that when we multiply by r, we're going to get ar to the n. And that's just going to keep on going. In fact, we're going to find, it's kind of bothering me that I left out this plus. We're going to find that every single term in the blue is going to match up with a term in the orange. The only thing that doesn't get paired up is this a. So that's kind of nice, because now if we decide to take those two equations and subtract them, well, the left side becomes s minus r times s. That doesn't seem all that complicated, I guess. On the right side, this is magical. A doesn't get paired up with anything, so that stays there. But ar minus ar is gone, is 0. Ar squared minus ar squared is gone. Everything else is gone. So we used to have this infinite expression involving s. Now we have this very not infinite, very finite expression for s. In fact, it's extremely simple to solve for s. We factor out the s, we're left with 1 minus r. You guys see where this is going now. And when we divide both sides by 1 minus r, we get the fantastic noble equation s equals a over 1 minus r. Amazing. So that is a proof for where this magical, super important formula comes from. Know it, learn it, recite it in your sleep. It is super important. We will use it over and over and over again. All right, so this is a very easy formula to use as long as we remember that a is the first term. Sometimes they're going to mess with you and n is going to equal 0. Sometimes n is going to equal 1. If we just remember that when in doubt, expand it out, look for that first term, and then look for that common ratio, the a and the r will not lead you astray. Okay, so let's talk about this this sum right here. This is clearly geometric. We're multiplying by 3 over 2 over and over and over again. As n gets bigger, we're multiplying by more and more 3 over 2s. 3's over 2's? 3's over 2? Anyway, r equals 3 over 2. And the most important thing to notice here is that that value is greater than 1. We're done. All we have to do is come to our conclusion. Therefore, the series diverges by the geometric series tests. The geometric series tests. Let's put the word test here so we can have the geometric series tests. All right. Anytime we come to a conclusion about whether a series converges or diverges, this case diverges, we want to state the test that we're using. This one is by the geometric series test. Perhaps we didn't do that with the telescoping because we were showing our algebra, but in general, we want to do that. All right. So this one does not look the same as this one, but it does look similar. And if you see what to do, then great. There's a quick way to do this. I'm going to do this the slower way. When in doubt, expand it out. The first thing we'll do is we'll expand it out and say 3 over 2 to the first term is going to be n equals 0. Then we'll do 3 over 2 to the 1, and then we'll do 3 over 2 to the 2, etc. And you're going to realize pretty quickly that this is 3, and then the next term is 3 times 1/2, and the next term is going to be 3 times 1/4. In fact, we're starting with an a value of 3 and an r value of 1/2. And what's the most important thing about our r value is which one of these two things does it, or equal to? Which one of these two inequalities does it fit into? And in this case, the absolute value of r is in fact less than 1, which is great because that means that we're talking about a converging sum. So not only do we say that the series converges, we can find what the series converges to. Therefore, the series converges to a over 1 minus r, so 3 over 1 minus 1/2. 1 minus 1/2 is 1/2. 3 divided by 1/2 is 6. So the series converges to 6 by the geometric series tests. And that's how the geometric series test works.